All right. First part of any measurement chapter, you need to learn what we call conversions. On your learning map, that's one of the skills that you need to be able to demonstrate. So you've done conversions like millimeters to centimeters, centimeters to meters, meters to kilometers. These are called length conversions. And then you've also done area conversions, which was exercise 4C. And the only difference between them is that it has the square, and also the numbers are now 10 squared, 100 squared, etc. Right? When it comes to volume, there are two types of volumes that we use, which is why, so you notice how I have volume and capacity there? Volume is the measure in metric units, or if it helps you to understand, just say length units, if that helps you, just in brackets, but metric units. Means that in metric system, not the imperial system, like UK, for example, metric goes in multiples of 10. That's why you found that going from centimeters to millimeters or to meters and kilometers, it always went up by an extra 0. So that's called metric system. So these are measures in metric units. So for example, cubic millimeters, notice the language I'm saying? I didn't say millimeters cube, it's cubic millimeters, cubic centimeters, cubic meters, okay? That is volume that you normally see that you would buy, say from Bunnings, or if you go buy bark, for example, if they're buying bark or stones, they would then be measured in this form. But sometimes, for example, if you're looking at a swimming pool and you're asking, well, how much space does a swimming pool have? The architects would not say, the volume, they'll say capacity. Capacity is the volume of liquids or gas. Okay, so they're both volumes, but measured in two different ways. One is measured in metric units, and one is measured in liquid or gas, which we talk about milliliters, liters, to kiloliters, to the capital M. Anyone know what capital M means? Megaliters. So this means mega. Okay, so megaliters. And again, it still works in that metric system. It's in tens as well, but they're two different measurements. One is liquid and gas. The other one is more length units. So here we go. How many mils in 1 liter? 1,000. For those who don't know. So you need 1,000 of these. So from milliliters, it's the other way. So from liters to meals, because you're going to meals, there should be a lot more meals. That's why it's times by 1,000. So 1 liter, times 1,000 to get to meals. Therefore, this would be now divide by 1,000. To go backwards, so from mils to liters, you divide by 1,000. How many liters in a kiloliter? That's what it feels like, but no. The nice thing is it's all thousands. So 1,000 of these liters will make 1 kiloliter. And one way to remember is like kilometers and then meters. So kilo is that 1,000. So 1,000 meters makes a kilo. Same thing here. 1,000 liters will make a kiloliter. Okay? So that means when I ask you, how many kiloliters would make a megaliter? 1,000. Very good. And then the reverse is just then divided by 1,000, divided by 1,000. So this one's a bit easier to memorize. It's all thousands. On the bottom, there are some common conversions that you can find. Laptops away, boys. You don't need that at the moment. You're writing notes. These are some common conversions. So when you get into a trade or so, these are some things that you should know as a prerequisite. Mils. 1 mil is equivalent to 1 cubic centimeter. What does that mean? I'll give you a visual representation and you can draw this as well. Back in primary school when you first learnt about place values and you got those little units and then you got those long sticks and then the big square. One of those units is measured to be 1 centimeter by 1 centimeter by 1 centimeter. So if you wanted to find the volume, so how much does that little cube can hold in terms of water, That cube, if you do 1 times 1 times 1, the volume, 1 times 1 times 1, that's 1 cubic centimeter. That's what this represents. It can fit 1 mil. So hypothetically, if you were able to get one of those cubes and it was empty and hollow, and you filled it with water, it should be exactly 1 mil. That's what 1 mil is representing. Okay? So that equals to 1 mil. Just to help you remember, one of those cubic units, okay, those unit place values, the ones that you did in primary school, that's 1 mil. So that means 1,000 mils, which you know is 1 liter, which if you bought milk, a carton of milk, sometimes it's 1 or 2 liters. 1,000 of those little cubes, 1,000 of them will make 1 liter. And then the last one, this is special. 1 kiloliter, which we know means 1,000 liters, is actually equal to 1 cubic meter. And you can prove that by drawing a big cube. And the only way to get 1 cubic meter is this is 1 meter, this is 1 meter, this is 1 meter. And then if you convert them to centimeters, that's essentially 100 centimeters by 100 centimeters. So if you times them all together, you get 1 million. That's 1 million, 6 zeros. That's 1 million. And if you times it together, that's 1 million cubic centimeters. And if you use your understanding of how to convert centimeters to meters, we know that centimeters to meters is divided by 100, but because it's cubed, you divide by 100 3 times. When you divide 100 by 3 times, see, 1 million, if you took 1 million, 1 million, 1, 2, 3, 4, 5, 6, divided by 100 once, divided by 100 again, divided by 100 again, so 3 times. That's why it's 1 cubic meter. Okay, so 1 million cubic centimeters is equivalent to 1 cubic meter. In logical sense, most people can't visualize what 1 million cubic centimeters actually looks like. This one's easier. Shh, boys. If you wanted to visualize this, this is literally one of your boxes that if you had to do a moving, if you ever moved houses, one of those big boxes, that's usually 1 by 1. So 1 step across, that's 1 meter, 1 step forward, that's how wide it is, and then imagine 1 step up. That is the box of 1 cubic meter. So when you go by bark and all that, that's what they measure. They measure in terms of cubic meters. So they'll ask, like, how many cubic meters do you want? That's the volume. And interestingly enough, it might not look that big, but if you're buying bark, probably 2 or 3 will fill up a space like a playground very easily. But that, I can see why when people don't know how to work out volumes, that's how I did it for my own little playground in my backyard. I just measured, like it was a weird shape. It kind of looked like this. It had like this. It was just like that, roughly. So I just did a quick couple of measurements, worked out the area, and then I worked out how deep do I want it to go, times it, worked out the volume, and then I did a bit of the calculations and I figured out how much cubic meters I truly needed. You know what's special? When I ordered 3 cubic meters, and it fit exactly 3 cubic meters. Because obviously over time it's going to flatten, but when I poured it in, it literally was just right on the brim of where the what's that called, the wood thing, the barrier. Okay, so I had it, and it just filled exactly what I wanted. And I was like, only if my students could understand, the beauty of mathematics, where when you have something like this nice rectangle, you do the correct mathematics, you can actually roughly estimate what you need. So I bought exactly what I needed. I didn't have any extras, so that means I didn't waste money. But if I did have extras, I probably would have chucked at the front, find some bark area to chuck in. But that's the point. If you do a bit of logical thinking to do conversions, that's one of the benefits. Okay? All right. So far you've got your notes, how to convert water units or liquid units. That's also sometimes measured in gas units as well. This cubic meter, for those who aren't really strong with their metric, then copy this one down for volume. So how I did my conversions. Copy this one down. I'm just going to rub this one out. For volume, if you're not very strong, so you don't know how to convert cubic millimeters to cubic centimeters to cubic meters, so this is what I was doing to convert them to then work out. You can copy this down. So millimeters to centimeters, cubic, 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 and then backwards. From cubic millimeters, you divide by 10 cubed, divide by 100 cubed, divide, wait a minute, is that the right way? Sometimes I get this wrong. Centimeters, yes, it is divide 100 cubed, and this is divide by 1,000 cubed. This is times by 1,000 cubed, this is times by 100 cubed, and this is times by 10 cubed. Okay, so that's what I did. I measured it in centimeters first, because you know when you pull out your measuring tape, usually they measure in centimeters, not in meters. So I measured it in centimeters first. I worked out the area, and I got the area in centimeters. Then I times it to find out the volume in centimeters, but I had to convert cubic centimeters to cubic meters so that I go on the website and buy it. So that's what I did. I just went on the website, they asked me how much cubic meters I wanted, and I just did this conversion. I just converted that to that. Divided by 100 cubed. I got my number, did a rough estimate. I'm like, yep, cool. 3 should be enough. So they poured it 3, went to wheelbarrow it in, and it fits exactly in that space that I needed. Okay, so this kind of conversion you might use more often. From this to this. Worthwhile to know. All right, and this one's a nice one. When you are, this one I used, this 1 mil to 1, and this is not always true. If you do chemistry, you'll know that different liquids have different masses. But this one is useful. I used it for my daughter because she has eczema. We need to give her, the recommendation from the hospital is to use bleach baths, but you have to give it in a ratio. And one of the problems is that I needed, say, 10 liters. For every 10 liters, I needed just under 10 mils, so about 9 mils of bleach. The problem is that how do you get exactly 10 liters in a bucket, in a tub that looks like this? You know how like baby tubs, they kind of look like that? Like that. And it doesn't tell you how much it holds. And even if it does tell you, it doesn't have measurements to tell you if you get up to here, it's 2 liters or whatever. So when you pour it in, what do you use to pour in? You use a cup, use a bucket, use whatever you call it, you put it under a sink, and you pour it. The problem is, how do you know that's going to be exactly 10 liters? Now, if you want to do it, longest way is use a measuring cup. It tells you 1 liter, 1, 2. Yeah, so that's what my wife was going to do. I was like, nah, we don't have time to do that. So let's do a bit of maths conversion. She's like, I don't know how to do it. So I'm like, all right, I'll help you. The conversion is for every cubic centimeter, it's 1 liter. But you know what's an extra little piece of information that you might not know? For every, actually it should be, it's over here. 1 gram. 1 gram is equal to 1 mil. 1 mil is equal to 1 cubic centimeter. So write that in. Why is that useful? Because if you have 1 gram for 1 mil, 1,000 mils is equal to, or 1,000 grams is equal to. So another way of thinking about it is 1 liter is approximately, if we're not talking about masses in chemistry and all that, 1 liter of water is roughly 1 kilogram. Roughly. It just might be slightly off. So if I needed 10 liters, all I have to do, and the nice thing is my tub actually had a measuring weight on it already, but if you really wanted, put a weight scale, put the tub on, pour as much water until the scale reads 10 kilos. Because if it says 10 kilos, it's roughly 10 liters. And that was much easier for my wife to do. So I'll just say, oh yeah, just pour it in. When it reaches 9 or 10, you've got roughly about 10 liters. Okay, so that's what I mean. The benefits of knowing some of these conversions you can do as a practical. So what are some ones I just told you? I said this one is useful. 1 gram, 1 mil, 1 cubic centimeter. And just knowing how to convert those volumes there, that's another useful one. Okay, so that's when you're buying stuff later on, online, cubic meters. And that one there is the one that you would use for water. Cool. All right, team, let's move on. So today's lesson, that was one part. I mean, you didn't have to hear my life story on that, but I thought that would help you to gel it in, to sort of remember it, because it helps you when there's a story to it. Let's look at today's lesson. H&I, there's only one formula you need to know. Copy this down. Volume is equal to area times height. Now this area, can you write underneath it? It's not just any area. It is what we call a cross-sectional area. What this means, for those who don't understand yet, cross-sectional, boys, thank you, let's pay attention. So this part is important or key to understand the theory. You see, the cross-sectional means this formula only works for prism-like shapes. Now, what's a prism? See, if you drew a triangle, that's 2D. And then if you think about it, if I add a third dimension to it, I elongate it through the page, then I get a 3D shape. But it started off with 2D. This is your 2D. This is the 2D area, so two-dimensional space, it's flat. But as soon as you add a third dimension to it, you get a 3D shape, right? So this is your third dimension. What's a cross-sectional area? It means that once you have this shape, if I cut it, no matter where I cut it, just picture it like a Toblerone chocolate. If I cut it and then I separate it, right? If you separate it, notice the shape here in those two pieces. If I separated them, one will look something like this, and the other one will look something like this. True? Separating the two. But notice the faces are exactly the same. So if the faces stay the same throughout, no matter where you cut and separate them, that is called a cross-sectional area. That's what makes a prism. See, a prism is the idea that no matter where you cut it, the faces at the front and back is always going to be the same. That's why a cylinder, if you think about like a sausage or a pipe, when you're cutting pipes, so no matter where you cut, wherever you cut the pipe, the front and this one, no matter where you cut, is always the same shape. That is called a prism. Okay, and that means the formula works as if you know the 2D area and then you times it by the third dimension, that's how you get the volume. Because you're looking at how much space does it occupy, and then what if I took that space and then elongated it out? That's why you times by the third dimension. Okay, so you take the area, how much space does it occupy, and for how long? That tells you the space that's available. Okay, so that's why the formula only works for anything that is a prism. That's why it doesn't talk about pyramids. See, pyramids, if you cut it now, see if I cut the top and I cut the bottom, the shape gets smaller as I go up, the shape gets bigger as I come down. So that top face and bottom face is always going to be different. That space on the bottom here could be a rectangle, and this could be a rectangle, but that rectangle is smaller than the rectangle on the bottom. That's why there's a different formula for pyramids versus prisms. Okay? Now, the most infamous volume formula that almost every student knows, even if I ask the foundation students, they still know, is the volume of a rectangular prism. What's the volume of a rectangular prism again? Length times width times height. This is the one formula that for some reason, when I ask, even if I ask what's the volume of a sphere, I still hear kids tell me length times width times height. Because it gets drilled so much that they just memorize that. But they actually don't understand what's actually happening here. If you actually look at the formula, have you noticed? Notice here, length times width. That's the area of a rectangle. That's the area, if you look at the width and length here, you're actually just finding the base area there. See that? You're just finding the area of the bottom, which is a rectangle. It's 2D. Why do you times it by height? The height is the third dimension. So you take how much space does it occupy on the bottom, and then by how long? So you pull it up and say how much space does it occupy if you times it all the way up? That's why it's H. That's why that formula that you learnt in primary school really... Boys, thanks. That's why this is technically... Girls, thank you. That's why it's area times height. Okay, so area times height is really all I want you to understand. So why am I harping on that? Is because the next exercise that you do, I find that students are used to doing this one. They can do this question without a problem. They'll do, oh yeah, I know how to do this one, sir. 3 times 4 times 5, and they type in the calculator, they get 12 times 5, they get 60 cubic meters, and they feel, yep, I'm pretty good. Shh. The problem is this one. And really, if you understood what I was just explaining just now, that this one shouldn't throw you off. See, this one, when I first give it to students, especially the ones who don't listen to what I'm explaining and not understanding what I'm really trying to get them to see, they look at this and they go, no, I have no idea. But it was literally what I was just describing. See, that shape there, I don't know what that shape is, but I do know one thing, that's a prism. No matter where you cut horizontally, the top face and the bottom face is going to be the same. So if it's a prism, all I need is the 2D area, then times it by the third dimension. That's all it is. They already just told you the area. They told you this space is 11. Here's your third dimension. You're elongating that much. So you're going to find that 2D. Where is that consistent area that stays the same? Well, it's here. And you're elongating it all the way down. So it's like that flat, and you're pulling it down. So it's really just 11 times 4, which is this formula, area times height. We already know the area, cross-sectional area is 11 by 4, 44 cubic centimeters. So even when you're starting to do all these shapes, notice even the formula for a cylinder, you just need to find the cross-sectional area. It's this one. It's the flat circle that is consistent throughout the shape. And what was the area of a circle again? 4E and 4F. What's the area of a circle? Beautiful. So if I want you to find the volume of a cylinder, all you needed was find the area of this 2D circle and then elongate it by the third dimension. That's my height. So, put it all together. This is the formula. That's the formula for the volume of a cylinder. Technically, I've given you the Year 9 version of it. Usually Year 8s only do pi r squared h, but I'm actually giving you the part so that you understand. This is the circle, and this is the third dimension. That's it. This is the area of a 2D shape. Does that make sense, what I'm trying to explain? Yeah, 2D area by the third dimension. That's all it is. That's what volume means. Get the area of a 2D shape. If it stays consistent, times by the third dimension. And that's what 4H and 4I is. That's all it is. Eventually, you're just going to work with different random shapes. You get different parts of the shapes, but your aim is to find the area of the cross-section first, times by third dimension. Okay? So that's quite a bit of theory. I'll probably pause there so that you can have some time to practice H and I. Tomorrow, what do you have to bring?
Charge laptop.
Charge laptop. You've got a PAT for maths. You can bring a scientific calculator as well. So bring that so that you can work on it. You'll have about 45 minutes to 50 minutes to complete the task.
What is it about?
Maths.
Like everything?
Yeah, I think they do general testing because they just want to know. And usually these PAT tests would do things like from year 7 to year 9 maths, usually. So you get a range of them. Some things you'll know and then some things you don't. That's just... Okay. All right, team. I'll stop the video there.